Today you're going to learn about the physics behind photonic crystals. Photonic crystals are comprised of two basic concepts. Photonics, meaning the study of light, and crystals, which are periodic lattice structures. Therefore, photonic crystals are defined as periodic structures that have bands that forbid the propagation of certain frequency range of light. This phenomenon does occur naturally in nature, such as opals and butterflies. However, humans can synthetically design these crystals to adjust the frequencies that are reflected or seen by the naked eye. So to truly understand how photonics work, we're going to cover the properties of light waves. Now, light waves can be altered in 4 different ways. They can be reflected, refracted, diffracted, or scattered. Reflection is when light waves hit an obstacle and bounce off at an angle. Reflection is just like looking in a mirror, and your image is reflected back to you. Refraction is the bending of light waves in an alternate angle from the original pathway. To imagine refraction, think of a straw in a glass of water. When you look at the straw, it looks like it's been broken into 2 pieces. The light waves that travel through the water are being bent, so the straw looks broken. Diffraction is the bending of light waves around an object or particle. Diffraction is a special circumstance of scattering, where the wave as a whole is unaffected. Scattering itself is when light waves come in contact with a particle and it causes the individual wavelengths to travel in separate directions. Light that comes in contact with the crystal is either reflected away or continues propagating through the crystal. Now we see color around us every day in the form of visible light. When light strikes an object, the frequency of its waves does not always match the natural frequency of the vibrations in the medium. This causes some of the light to be reflected from the object, while the rest is absorbed.
The way this functions in photonic crystals is that when a light wave comes in contact with the crystal, certain frequencies are reflected away, while the rest is propagated through the crystal. This can be seen naturally in butterflies. Butterfly wings contain microscopic photonic crystals that cause certain frequencies to bounce back, giving them a certain color, while the rest of the light frequencies are unaffected and absorbed into the wings. This gives butterflies their vibrant colors because the bands are so small that only a single wavelength is reflected back for the eye to see. Now you're probably wondering, what are bands? Photonic crystals are composed of extremely small bands alternating with gaps between them. These can be set to specific widths so that certain waves bounce off and away from the structure. You can calculate the energy level of these bands using the wavelength of the waves you want to reflect. This is in the equation E equals hc over lambda, where E is equal to the gap energy of the band gaps in joules, H is Planck's constant, C is the speed of light, and lambda is the wavelength. Qualitatively, this shows that the energy of the band gap is inversely proportional to the wavelength of light. The greater the band gap energy, the smaller the wavelength. To determine the energy of the band gap needed for a specific frequency to be reflected, frequency can be substituted into the equation in place of wavelength. From the equation, lambda equals V over frequency. Here's an example of a problem that you might use this equation for. If the wavelength of the wave you want to refract through the band is 210 nanometers, what is the energy of the band gap? We use the equation previously stated, which is E equals hc over lambda. We plug in Planck's constant, which is about 6.626 times 10 to the negative 34th meters squared kilograms per second, and the speed of light, which is 299,792,458 meters per second. And the wavelength was already established as 210 nanometers, which we can convert to 2.1 times 10 to the negative 7th meters. After we plug everything into the equation, we end up with 9.459 times 10 to the negative 19th joules. This goes to show how the width of the bands in the photonic crystals can be calculated to correspond with specific wavelengths and frequencies.
Photonic crystals exist in 1, 2, and 3 dimensions. The main difference between these 3 types is how light waves are able to travel through the crystal. In a one-dimensional crystal, the bands exist in stripes. As the pink light hits the bands, it continues propagating through the crystal. The orange light, however, is refracted outwards. Light could not exit through the top or bottom of the crystals since there are layers of bands blocking the light's path. 1D crystals are used in optical lenses and some color-changing paints. Pretty cool, right? In 2D crystals, the bands no longer look like bands. Instead, they are more like vertical columns. The band gaps between the columns look like holes. Light can now pass through the crystal going from top to bottom. The pink light is emitted towards the crystal from the sides and from the top and continues moving, while the orange light is refracted at both angles. 2D photonic crystals have been made into optical fibers, but we're not really sure what those are. In three-dimensional crystals, there are vertical columns and horizontal columns of bands occurring in three directions. Light can exit or refract through the crystal in all directions. 3D crystals can be found naturally in opals, but we're not really sure how we can use these in industry yet. Recently, scientists have been wavering between the three types of crystals and now are trying to manipulate 2D crystals to apply them into LED lights. LED light bulbs are sweeping the nation with their energy-efficient technology, replacing incandescent light bulbs with a brighter design. But even though 70% of the electrical energy supplied to a typical lighting diode gets converted into light, only about 20% actually leaves the bulb. Why is this? As the electricity supplied to the bulb moves from the cathode to the anode, some of the energy gets lost as radiation from the emitter chip. When this happens, a lot of the light gets trapped inside the chip and never sees the light of day or darkness of night. So what can we do to help the light escape? Since we are able to design photonic crystals that reflect certain frequencies and allow others to pass through, we can apply this to the LED technology by etching photonic crystals into the emitter chip. These crystals would be designed so that a smaller amount of frequencies are affected by the bands. This way, more light is able to leave the emitter chip and escape to the outside surroundings of the bulb. LEDs would be a whole lot brighter. But like we've said before, photonic crystals can be applied or discovered in more than LED bulbs. It seems as though they are expanding research opportunities and marketable product ideas for the near future. So let's review. Photonics means light, and crystals means lattice structures. Together, these make photonic crystals, lattice structures that interact with light. We saw that light can be reflected, refracted, diffracted, and scattered, and that photonic crystals rely on refraction to manipulate the movement of light waves. This occurs due to the bands in the crystal structure. Some waves are allowed to continue propagating through the crystal, while some are refracted in a new path. These bands can be calculated with the equation E equals hc over lambda, E being the energy of the gaps between the bands, h being Planck's constant, c being the speed of light, and lambda being the wavelength of the specified light wave frequency to be refracted. Photonic crystals can come in 1, 2, and 3 dimensions, each having their own unique properties regarding the directions light can be refracted within and outside of the crystal. And we now know that 2D crystals could be utilized to improve LED technology and create brighter bulbs for the marketplace. Photonic crystals are truly remarkable, and now you understand how they work.